Hello and welcome to this video tutorial of Air Force Research Laboratory's Origami Topology Mechanism Optimizer. Below this video window is a link to MATLAB Central where you can download the program. To begin, simply run the Start program. Here's the interface of the Origami Mechanism Topology Optimizer, or OMTO for short. You can see the four main buttons on the left: Problem, Save Problem, Optimization, and Save Results. To begin, click Problem. The grid already contains the so-called chomper problem, which is detailed more in the user guide. In this tutorial, we will be solving a different problem, one that involves a dome-like fold solution. We'll change the dimensions of the grid by clicking New Grid. You can see this dialog box shows the other choices of grid types. We'll keep the first one, change the number of Y units to 4, and the Y sheet size to 2. Click OK, and there's the new grid. Now we can specify special nodes. We'll start with boundary conditions, choose fixed. After clicking on a node, we can specify the displacements we would like to fix. At this node, we will fix all. To signify that, we'll keep a 1 in each box to show we're fixing every degree of freedom. We're going to continue fixing nodes. We'll fully fix one more node. And then this node we want to be able to slide in the XY plane but not move in the Z direction. So we'll put zeros in the X displacement and the Y displacement boxes but keep a 1 in the Z. And then we'll do the same in one more location. So we'll add one more slider there. Now we are finished fixing nodes and we'd like to implement some matched boundary conditions. So you go to BCs and then matched BCs, choose this source node and that matched node, and here we can choose which displacements are matched between the two nodes. We're interested in matching the Z displacement. These matched boundary conditions are particularly useful in enforcing symmetry in the model and in preventing rigid body motion. We'll also put two more matched BCs over there. Next, we'll specify forces, so click Fn. The forces we're implementing are downward, or into the screen, so that's the negative Z direction. So we'll put a -1 in the Z. We're putting these forces at all the locations of the matched nodes. Now that we're done placing forces, we can specify the magnitude of these forces, which we'll keep at 500. The last special nodes we need to implement are the output displacement nodes, or the objective nodes. The objective in this problem is to raise the center point as high as possible, so we'll click U out, choose the center point, and the positive Z displacement direction. Now we are done creating the problem, so we can save it. Click Save Problem, then Save.mat. This saves the parameter file, allowing you to load it at a later time if need be. We'll also save the figure displaying the grid and nodes. To demonstrate the usefulness of the load button, I'll go back to the problem interface and clean the grid to remove all the nodes. Now if you go back to load, you can load the file that we just saved, and there it is. There's one more detail I should mention about the problem interface. The remove button lets you remove properties from nodes, which can be helpful after making mistakes like adding a node you didn't want. Now on to optimization. Under settings, we can set the max number of iterations. We'll use 100. And we can also set the allowed fold line fraction, which is the fraction of the grid fold lines that the solver is allowed to implement. Let's keep it at 0.3. We begin the optimizer by clicking Run. The optimization dialog box pops up and begins to iterate. This plot is produced by the MATLAB fmin-con optimizer, which is part of the MATLAB optimization toolbox. The optimization is finished, and you can see the solved crease pattern, a plot of the objective as a function of iterations, and the folded final state. You can also rotate and zoom on these plots. Lastly, we'd like to save the results. Click Save Results. From here, you can save the crease pattern on the top left, the objective plot on the top right, and the folded pattern on the bottom right. You can also save all of them at once. After clicking All, you select the location and type a root name for the files. The program saves all three figures. Going back into MATLAB, we'll find those three files. There's the three figures right there with the different endings on the root name that we specified. So that's all. Thank you for watching. If you have any questions or feedback, don't hesitate to contact us. Thank you.